Chapter 4, Motion. This lecture will help you understand two-dimensional motion and the range of a projectile. The motion diagram shows a ball rolling across the table. Ignoring friction, there is nothing to speed up or slow down the ball, so it moves with a constant velocity. If a ball is simply dropped from the edge of the table, it will accelerate toward the ground, picking up speed and covering a greater and greater distance as time passes. This schematic shows the positions of a ball being dropped and being projected horizontally at the same time. The blue arrows indicate its vertical motion. The yellow arrow, its horizontal motion. The blue arrows show the increasing speed and the increasing distance as the ball is dropped. The yellow arrows are constant. The combined motion at each instant is given by the red arrows, which is the vector sum of the blue and yellow arrows. The resulting motion is the curved path shown, known as a parabola. Here are a series of photos showing that a dropped red ball and a yellow ball projected horizontally from the same height at the same time fall vertically at the same rate, and so they hit the ground at the same time. Velocity vectors are shown as a ball kicked into the air travels through its trajectory. Note that the yellow horizontal component remains constant at each instant, while the blue vertical component decreases as the ball rises until the ball reaches its peak, at which the vertical component is 0, and then the vertical component increases as the ball falls. The use of A, S, and V is ambiguous since we can have motion in both the X and Y directions. We need to improve our notation so that we avoid confusion. We introduce the following notation. Delta X, or delta S sub X, is the motion in the X direction. Delta Y, or delta S sub Y, is the motion in the Y direction. V sub X is the velocity in the X direction. V sub Y is the velocity in the Y direction. V sub Ix is the initial velocity in the X direction. V sub Iy is the initial velocity in the Y direction. V sub Fx is the final velocity in the X direction, and V sub Fy is the final velocity in the Y direction. A sub X is the acceleration in the X direction, and A sub Y is the acceleration in the Y direction. As an example, a ball rolls at constant speed of 0.700 meters per second as it reaches the end of a 1.30 meter high table. How far from the edge of the table does the ball land? The data are given in the problem description. Delta S sub Y is negative since the motion is down. We are trying to find the horizontal motion before it hits the ground. We will need two basic equations. Delta S sub Y, our position in the Y direction, is V sub Iy times delta t plus 1/2 A sub Y times delta t squared, and delta Sx, our change in position in the horizontal direction, is V sub x times delta t. The time intervals for the two motions are the same. We rewrite our two equations, the first being solved for delta t, which is the square root of 2 times the change in motion in y divided by the acceleration. delta S sub x is v sub x delta t. The horizontal velocity, v sub x, is constant throughout the motion. Substituting what we know, delta t is 0.515 seconds. Delta s then becomes our horizontal speed of 0.700 meters per second times our time, 0.515 seconds, giving us a total distance of 0.361 meters to 3 significant figures. A baseball is hit and moves initially at an angle of 35 degrees above the horizontal with a velocity of 25 meters per second. What are the vertical and horizontal components of the initial velocity of the ball? How long will the ball be in the air? And what is the range? We make the simplifying assumption that the ball is hit at ground level and that the ground is level. Also, there is no air friction. The initial speed and angle are given in the problem description. The basic equations are the x and y components of the initial velocity and the change in velocity in free fall and uniform horizontal motion. What are the vertical and horizontal components of the initial velocity of the ball? These are just the x and y components of a right triangle. We use v for the initial speed of 25 meters per second and an angle of 35 degrees. Substituting these and noting that both components are positive, we get a uniform horizontal velocity of 20.5 meters per second and an initial vertical velocity of 14.3 meters per second. To find how long the ball will be in the air, we will use the working equation. Delta t is v final in the y direction minus v initial in the y direction divided by minus g. The initial velocity is 14.3 meters per second upwards, so must be positive. Our final velocity, ignoring air friction, must be the same but traveling downwards, or negative. The initial velocity in the y direction we found as 14.3 meters per second, so the final velocity just before it hits the ground is minus 14.3 meters per second. The total time is 2.92 seconds to 3 significant figures. What is the range? Our working equation is delta x is v sub ix times the time interval. This is just the distance traveled at a uniform horizontal velocity of 20.5 meters per second. We know the horizontal velocity and the total time before the ball hits the ground, so the horizontal distance traveled is 59.9 meters to 3 significant figures. Now we will look at a set of problems for you to work on. Pause the video to give yourself time to work on these problems. Heather and Matthew walk with an average velocity of 0.98 meters per second eastward. If it takes them 34 minutes to walk to the store, what is their displacement? Pause the video while you work on the problem. Did you get 2,000 meters east? If Joe rides his bicycle in a straight line for 15 minutes with an average velocity of 12.5 kilometers per hour south, how far has he ridden? Pause the video while you work on the problem. Did you get 0.1 kilometers south. It takes you 9.5 minutes to walk with an average velocity of 1.2 meters per second to the north from the bus stop to the museum entrance. What is your displacement? Pause the video to work on the problem. Did you get 680 meters north? Simpson drives his car with an average velocity of 48.0 kilometers per hour to the east. How long will it take him to drive 144 kilometers on a straight highway? Pause the video. Did you get 3.00 hours? What is the acceleration of a car that moves at a steady velocity of 100 kilometers per hour for 100 seconds? Pause the video to work on the problem. Did you say 0? For no change in velocity occurred. Misreading the question might mean missing the word steady, which of course means constant or no change. For a freely falling object dropped from rest, what is the acceleration at the end of 5 seconds? At the end of 10 seconds? Defend your answers and distinguish between velocity and acceleration. Pause the video. Did you get, for a freely falling object, acceleration is constant? Acceleration is approximately 10 meters per second squared, all the way down. Velocity, however, is 15 meters per second at 5 seconds and 100 meters per second at 10 seconds. Emily Easygoat can paddle a canoe in still water at 8 kilometers per hour. How successful will she be at canoeing upstream in a river that flows at 8 kilometers per hour? Pause the video to think about the problem. Did you say Emily will not be successful because her speed will be 0 relative to the land? Find the acceleration of a hamster when it increases its velocity from rest to 15 meters per second in 1.8 seconds. Pause while you work on the problem. Did you get 8.3 meters per second squared? Find the distance that a freely falling rock drops when it falls from rest for 2 seconds. Pause to think about the problem. Did you get 20 meters? Your Chapter 4 homework is due February 9th. There is an Apollo 15 video to watch on Blackboard if you have not done so already.